Alright, let's go over the, hi Discrete Math, let's go over the rest of the problems. Hopefully this will be a very short video. There were 7 problems that I asked you to do last week. I'm going to make you hand this in like very, very soon. So let's go over the 4 that we didn't go over. In class 3, 6, 12, and 24, let's do it. 3 was a little bit of an interesting problem. It said, find the error in the proof of the given claim. So, Gossett is telling us that we should not just be good proof writers, but good proof readers, and we shouldn't get tricked. And, as I mentioned today in class, sometimes I get kind of excited, and I write my own proofs, and sometimes they're wrong. So you should be very, skeptical at all times because, even your teacher, Mr. Rose, math genius, is sometimes wrong and presents mathematical arguments which are just simply invalid and make no sense. So you should, be on the lookout at all times to be looking at every step and deciding whether it's true or false. Okay, let's build that skill. Well, this proof is wrong. Why? And is it salvageable? Well, the theorem says that the supposed theorem, the claim, is that if A divides B and B divides A, then A equals B. That's certainly very plausible. Hey, if 2 numbers are each factors of each other, then they must be the same number. Okay, let's see if it's true. Well, let's look at the proof. What's the proof? It says if A divides B, then using the definition of divides, then B must be some multiple of A, so B is AK for some integer K. And since B divides A, similarly, A must be a multiple of B, so A is of the form Bm for some integer m. Well, if that's the case, then B I can write as AK, and in place of A I can substitute Bm, so B is just Bmk. So if B is just Bmk, then the only way for that to be true is if Mk is 1, and if Mk is 1, then M and K must both be 1. But wait, no, I found the error. It is right here. I cannot conclude that just because M times K is 1, that M and K are both 1. What if, alternatively, since M and K are integers, M and K are both -1? So I'll even maybe just write that down, but it's possible that M is -1 and K is -1. And if that's the case, then this simply doesn't follow. And in fact, so not only have we found the error in the proof, we've shown that the inference from Mk equals 1 to M equals K equals 1, though seemingly very innocent, is in fact, that's an invalid inference, simply not true. Counterexample, M and K could both be -1. And that makes me now look anew at the theorem, because, well, what does it mean if M and K are -1? Well, it means that B is just -A, and A is just -B. And now that I remember that, negative numbers exist, or something like that, then I'm ready to say that this theorem is actually just false. Because, and here's a counterexample, we could have led with this, but this theorem is false because, well, for example, 5 divides -5, and -5 divides 5, but that does not make those numbers equal, so, okay. Good, that was a nice little exercise, boom, boom. And here we sort of decided here I chose the path of finding the error in the proof, and then using that error in the proof to construct a counterexample to the theorem. But you could also have taken the other tack and just thought about the theorem and tried to find a counterexample to the theorem, and then that will give you some indication of which one of the steps of the proof must be wrong. So there's kind of a give and take when it's much harder. It's a very kind of high intellectual activity, I think, to scrutinize a proof to see if it's invalid or not, and you need to do this with your own proofs, to see if they make sense. And so there's this back and forth between trying to find counterexamples, trying to do proofs, seeing if your proofs are valid, seeing if you can find counterexamples. All right, pushing on. 6 is just a silly problem. What does 6 say? It says every rational solution okay, I'll actually write it out. Every rational solution of x squared minus 2 equals 0 is an integer. Okay, to make a little bit more clear what's going on here, what is being proposed is that for all x, if x is rational and x squared minus 2 is 0, then x is an integer. That's really the theorem written out more clearly and unambiguously in the language of predicate logic. And this theorem is true, and yet the proof is considered to be trivial. Why is the proof trivial? Because the proof is a conditional, but the antecedent of this conditional is simply false. This is false. Why is this false? Because if x squared minus 2 is 0, then what we have is that x is rational, and also that x is the square root of 2. But we have proven a couple classes ago that the square root of 2 is not rational. Therefore, you can't have a rational solution to x squared minus 2 equals 0. The antecedent is false, and so anything you claim in the consequent is irrelevant. The conditional is automatically true. And so this is a true theorem, but it's a silly theorem. So, because it's just sort of contentless. It's vacuously true, as they say. All right, moving right along here. Number 12 says, let A and B be real numbers with A, so A and B be real numbers, and let them both be positive. Use a direct proof, so show that A plus B over 2 is greater than or equal to root AB. And all right, I don't know what use a direct proof means exactly. You know, just show that this is true. Okay, how? Well, this is actually a problem that I assigned in Pre-Calc C. So you did this, and maybe in functions as well. You did this problem. How can we show this is true? Well, oftentimes when you need to demonstrate something with inequalities, it helps sort of work backwards. So let's now work backwards by multiplying both sides by 2. And of course, not only is multiplying by 2 equivalence preserving, but not only is multiplying by 2 legitimate, but dividing by 2 is also legitimate. Therefore, this sentence I'm trying to prove is in fact equivalent to this second sentence. And therefore, this is, if this is true, then this is true, and sort of vice versa. So if you pursue only equivalence preserving operations, then maybe, well, let's just keep going and see what happens. Well, I can square both sides of this. That seems what we need to do to get rid of this square root. So if I do that, I get a squared plus 2ab plus b squared is greater than or equal to 4ab. Is it legitimate to square both sides of an inequality? Well, as long as everything is positive, then yes. So if some number is bigger than some other number and both of the numbers are positive, then so are their squares greater. And if two perfect squares are in a certain kind of relationship with each other, such that one is bigger than the other, then their positive square roots also are in that same relationship. So once again, we have equivalence kind of in both directions. Alright, well now I can subtract, and I get a squared minus 2ab plus b squared is greater than or equal to 0. And okay, here I just performed a subtraction, so that is perfectly equivalence preserving, and this is says that a minus b squared is positive. So this is just true, man. So if you want to write like, true, then this is how you do a proof backwards, but also don't write any more additional comments, because I think this is perfectly legitimate. If it's really true that every one of your steps is equivalence preserving, and you add in this kind of like equivalence symbol here, then everyone knows when they see a proof written like this that they should sort of read from the bottom up, right? I showed that this was true by showing that it was equivalent to something which was true, which is that every perfect square is greater than or equal to 0. Okay, so good. The last one, number 24, is like very tedious and therefore, well, kind of depends on your personality, I suppose, or your mood. Kind of very exciting, because the very notion of proof is that we can establish, facts which are even sort of very, very obvious somehow, that we can still prove them. That's kind of exciting. But I don't know if this proof is that much fun. But anyway, someone's got to do it, so it might as well be us. What are we proving? We are proving the triangle, the so-called triangle inequality. Right, in period 8 today, I started this proof quite a bit, but in period 9 I didn't. Yeah. So kind of get the classes back together now. What was this? Number 24. And yeah, it just says, take any two real numbers. So let x and y be real numbers. And here's the theorem. The theorem is that the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. This is sort of a fact about vectors or something like that. If you want to think of real numbers, positive and negative real numbers as kind of one-dimensional vectors, then this is stating some fact. It's called the triangle inequality, kind of for that reason, that if you take it in two, make sure I don't embarrass myself here. I guess, what is this? This is like x, and this is y, but then this is like x minus y or something like that. No, okay, sorry, hold on, I got this now. Duh. This is x and this is y, and this is x plus y. So in two dimensions, this is saying that this is why it's known as the triangle inequality. That's what I'm explaining here. That x plus y is always greater than or equal to x plus y. Where here we're thinking of the size of the vectors, so sort of the lengths. Okay, but anyway, we're just proving with real numbers, so this is sort of the the one-dimensional version or something like that. And okay, this is just kind of obviously true. The one line, I'm not going to write it out, proof of this, just says duh. If they're all positive, then it's just duh. But if x and y are negative, well, the absolute values, make them positive again. But here, if they have opposite sign, then, the number's getting like smaller magnitude-wise. So that's kind of the intuitive explanation. But okay, if we're going to really prove this, then we're going to prove it, based on something. Well, based on what? Based on sort of very low-level properties of real numbers and based on the definition of the absolute value. So let's get that out of the way. What is the definition of the absolute value? Well, one can give a definition. It's the definition you've heard in middle school, 9th grade, 10th grade, and now it's the same old definition, that the absolute value of z is a piecewise thing. It says, okay, look on the inside, see if that thing is positive or negative. If it's positive, then, so if z is greater than or equal to 0, then the absolute value of z is just z, but if z is negative, then the absolute value of z is just negative z. So, keeping this in the background, what we're going to ultimately do is like decompose these absolute values into, by cases. And so what now seems to be going on is like some dizzying number of different cases. And okay, there are different approaches you can take here, but my approach was to consider all the cases in which x and y are positive or negative. But then also, that sort of wasn't enough, right? Because I also cared about which was bigger, x or y. And so what I did now, as I explained today in period 8, is I said, without loss of generality, let the absolute value of x be greater than or equal to the absolute value of y. So let's just agree that x is the bigger one. Okay, certainly, there are a lot of different ways to think about this. Certainly x and y, this is x plus y, this is normal addition of real numbers, it's commutative. So, x plus y plus x is the same thing. So, just see which one of these is bigger, and whichever one's bigger, call that one x. That's one way of thinking about it. So in other words, like change the labels or something like that. Another way of thinking about this without loss of generality, well, when people say without loss of generality, what they're really saying, as I explained in period 8 today, is, do a proof by cases, but don't really do it. in other words, it's just a fact that given any two numbers, one's got to be bigger, or they're the same. So x is greater than or equal to y, or y is greater than or equal to x, size-wise. And so, or both, in fact, if they're equal. Therefore, everything that I'm about to do is going to apply to this case, but this case is just the exact same thing, with the letters reversed. And so we're doing sort of one case of a proof by cases, you might think of it this way, and we're neglecting the other case because it would just be totally repetitive. Okay, keeping that in mind, I'm now ready to begin. Okay, let's begin. Well, I now claim that there are 4 cases. There is the case where x and y are positive. So x is greater than or equal to 0, y is greater than or equal to 0. Let's call that case 1. Then there is the case 2, where x is positive and y is negative. Then there is case 3, where x is negative but y is positive. And case 4, where x is negative and y is also negative. Now, are some of these cases also repetitive? Yes, very much so, but still nonetheless I'm going to do all 4 of these cases now. And ultimately, now having made assumptions about the sign of x and y, and also having made assumptions about the relationship between x and y, I'm now in a position to tell you for each of these 3 absolute values, whether the inside is positive or negative. And hence I'm going to get rid of all the absolute values. That's the strategy. Let's do that first. Okay, let's go over here. Suppose x and y are both positive. Well, first of all, if x and y are both positive, then that means that the absolute value of x is just x. I keep saying positive, but really I mean greater than or equal to. And it's also true that the absolute value of y is just y. And it's also true that if x and y are greater than or equal to 0, that x plus y is greater than or equal to 0, because that's like a thing. And therefore, the inside of this absolute value is positive. Therefore, the absolute value of x plus y is just x plus y. Good. Well, what does that mean? It means that the theorem that I'm actually trying to prove, therefore, restated in this case, is just the theorem that what is the absolute value of x plus y? It's just x plus y, and this is just x, and this is just y, and so that's just, that's just true, because they're equal. Case 4 is very similar. If x is less than or equal to 0, I guess I now realize that I should be more careful. All these negatives should be like that, I guess, is better now. Yeah, that's better. La 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 la. Well, if x is negative, now what? Well, since x is negative, then the absolute value of x is in fact just negative x. And the absolute value of y is in fact just negative y. But, so this is kind of a different case, you might say. Also, if I add two negative numbers, then I know that what I get is negative. So, the absolute value of x plus y is in fact just the opposite of what's on the inside. So it's negative x plus y. Therefore, the theorem that needs to be proved in this case is that the absolute value of x plus y, which reduces to just negative x plus y, is less than or equal to absolute value of x, which is negative x, plus the absolute value of y, which is negative y. And indeed, this just says that negative x minus y is less than or equal to negative x minus y, and that's just true. Okay, so those are kind of the two easy cases or something. Okay, now we go to case 2. And cases 2 and 3 are going to be very similar, but okay, a little bit different. What now? Well, x is greater than or equal to 0. So, the absolute value of x is just going to be x. And the absolute value of y is going to be negative y. And now I need to determine inside here whether x plus y is positive or negative. And okay, because x is the bigger one, then it's going to be positive. But here, note that I'm going to write every single step because, why not, right? If we're getting down this low, let's go all the way. Notice the thing that I know, right? What I know is that since the absolute value of x is greater than or equal to the absolute value of y, that was what I assumed at the outset of this problem, then what do I know? Well, the absolute value of x is just x, and the absolute value of y is negative y, so what I know is that x is greater than or equal to negative y. That can be interpreted, then, of course, if I add y to both sides, then that tells me that x plus y is greater than or equal to 0. So, in fact, the absolute value of x plus y is just x plus y. Therefore, what is the theorem that needs to be proved in this case? It's the theorem that the absolute value of x plus y, which is x plus y, is less than or equal to the absolute value of x, which is x, plus the absolute value of y, which is negative y. And that's true if and only if y is less than or equal to negative y, which is true if and only if 2y is less than or equal to 0, which is true if and only if y is less than or equal to 0, which is just true. Well, I guess I a little bit don't like this, but of course, because I'm in the case where, well, I know y is negative. Oh, so okay, so and we can even do this. So we can, if you want to be super fancy, you can now write like this. So in other words, note the direction of this arrow. So I have proved my theorem. Why? Because y is less than 0. Fact. Therefore, the arrow is pointing this way, y is less than or equal to 0. After all, that's law of addition. If y is negative, then it's less than or equal to 0. Therefore, 2y is less than or equal to 0. Therefore, y is less than or equal to negative y. Therefore, by adding x to both sides, we get this statement. And this is the actual theorem in the case, in this case. Okay, hopefully you're following all this logic. Whew. Good. The next one should be very similar. Now, maybe almost exactly the same, you might say, but maybe a little bit different because of this asymmetry induced by this assumption. So, okay, if x is negative, then the absolute value of x is just negative x, fact. And if y is greater than or equal to 0, then the absolute value of y is just y. So, let's now invoke our assumption that the absolute value of x is greater than the absolute value of y. So since the absolute value of x is greater than the absolute value of y, what does that tell me? Well, it tells me that negative x is greater than or equal to y. And that tells me that, it tells me this, right? That x plus y is in fact less than or equal to 0. And if x plus y is less than or equal to 0, so this really is a kind of a different case, then what does that tell me about the inside? It tells me that it's negative x plus y. So the absolute value of x plus y is negative x plus y. Okay, that's just legit because if x plus y is actually negative, then it's really the opposite of it. But if x plus y is 0, then, negative 0 is still 0. So that's totally fine. Okay, and now here we are. So having determined what the three pieces are, I now restate the theorem. What's the theorem? The theorem says that the absolute value of x plus y, which is actually negative x plus y, is less than or equal to negative x plus y. Is that true? Well, what does this say? This is negative x minus y is less than or equal to negative x plus y. So I can cancel the negative x's. So that's true if and only if 2y is greater than or equal to 0, which is true if and only if y is greater than or equal to 0, and that is in fact true. And so I'll just write like, true or something, and throw in some doubly things, and maybe not even bother. So, alright, what just happened? What just happened was, through the sort of 4 tedious cases considering the 4 possibilities regarding the sign of x and y, and also on the outset handling whether, just asserting that x is the bigger one, bigger in magnitude, we've shown that in all of these cases, this triangle inequality is true, and so it's true, and I never have to think about this kind of thing again. You can just tell people that you have proved it. Goodbye.